Let's get started. Get this done quick. So today we're going to continue to discuss this variance reduction technique. So we're going to study a new technique, method 5, called importance sampling. Right? So importance sampling, the general idea is that to sample the important region, to sample the important case, which is most commonly used for variance simulation. So recall that in the previous example, in this example, estimating the loss probability of an insurance company, our objective was to estimate the probability that the loss is greater than a large number, which is a rare event. Right? So our technique there was to create a large loss intentionally. For instance, y equals 3, y equals m, when m is large enough, we have mv, then we're going to have mv, then, we're going to have a large number of v, so it's more likely for the rare event to occur, right? The importance sampling idea is very similar, but in a different way, okay? So this is the basic idea. Importance sampling is often used to treat rare events. And we're going to intentionally make the rare event occur more frequently. So how rare can it be, right? And why do we care, right? So how rare can it be? Think about this example. Suppose your objective is to estimate a standard normal. The probability standard normal is greater than 20. That's very rare because the probability is very, very small, right? That is attributed to the very light tail of normal distribution. So this is a 20 standard deviation away from the mean. If you compute it, this is going to be 10 to the negative 89, extremely small. If you use crude Monte Carlo simulation, it's going to be painful because you have to generate at least 10 to the plus 89 many samples to get at least a 1, right? So on average, the sample size should be huge in order for one indicator to be 1, because that's the order of the rare event probability. Of course, this is another toy example. You don't actually have to do it because you know the exact value. But I'm just giving you an example, right? To obtain 1, y equals 1, you need an average of 10 to the 89. Okay. All right. So rare event can be very rare, right? Probability of rare event can be very small. Question then, why do we care, right? Can we simply say this is just 0, close to 0? Is it enough to know that it's close to 0? Answer, in this case we don't care because this is a toy example, but we do in many other cases. For example, one example is that if you have a nuclear plant, a nuclear reactor, you're wishing to estimate the probability that there's a meltdown occurring at this nuclear reactor in the next 100 years. This is a rare event. In most of the cases, it won't happen. But if it happens, it's going to be disastrous. Right? It's going to be catastrophic, right? So although theta is small, need to know theta to a high degree of accuracy. Another example, so in the application of financial engineering, suppose you're pricing a deep out of money pocket. a deep out of money option. You don't have to worry about what kind of option we're talking about. Just say an option with a strike price that is substantially greater than the current trading price, so the price of the option is small. In the order of cents. So this option is really, really cheap because it's unlikely that you can exercise, right? So the strike price is too high. It's unlikely for the market price to beat the strike price. Okay? So the price can be cents. Why do we care? It is going to be 0.1 cent or 0.15 cents or 0.2 cents. Because the bank may be able to sell a large number of shares, right? So that's why the bank needs to be accurate about the price, because many shares will be sold, right? So in many examples, you can actually argue that you want to estimate the rare event probability to some accuracy level. Okay. Okay. How rare can it be, and what do we care? Okay. Other examples, right? In practice, For instance, in telecommunication networks, loss probability of a small unit of information, which can be rare, and dependability analysis probability a system is failed at a given time can be rare. Air control system, what is the probability two aircrafts crash, right? So there's all other examples, right? These are all examples of rare event. In finance, this value of risk is very similar to that previous example that we talked about. The L is greater than a large number. The value of the risk is defined as the probability the maximum loss is greater than a threshold, right? Okay. So this is also a rare event simulation in finance. Remark. Typical probabilities of interest in this section are in the order of 10 to the negative 8 to 10 to the negative 10. So this is quite rare, right? Even for this, I mean, this is not as small as 10 to the negative 89, but in order to have a good estimate of this guy, you need to have at least a 10 to the plus 10 many samples. That's huge, right? Okay. Consider a rare event A. The raw or crude Monte Carlo estimator is the indicator. It is inefficient. Why? Look at the variance, right? This is a Bernoulli random variable. Its variance is equal to p times 1 minus p. But 1 minus p is so close to 1, so it's nearly p. Okay? Because p is so small, right? 1 minus p is nearly 1. So variance is very close to its mean, right? The mean is PA. So think about confidence interval. The mean is 10 to the negative 10, then the half width of the confidence interval is in the order of the square root of the variance, which would give you 10 to the negative 5. The mean is 10 to the negative 10, and the half width is 10 to the negative 5, then there's a significant overlap with the negative half line, right? So if you say I want to have a relative error gamma equals 0.05, that requires me to have the square root of the variance over n, which is the sample size, is close to 0.055% of the mean, implying that n is equal to 400 divided by PA. You can just plug it in and see, right? Just take the square of both sides and see. And what is this, right? PA is already very small, and n has to be 400 times 10 to the plus 10. Huge, right? So this is a reasonable relative error. This is reasonable. This is not too bad, 5%, but this is going to be huge. This is huge, right? So rare event simulation is an important branch of the field of simulation. Many people actually conduct research in this area, in this sub-area of simulation. Okay. Let's consider a toy motivating example. Suppose x, y, this vector, is uniformly distributed inside a unit square. Okay, so I have a unit square, I have x, I have y, which is the random point. It's uniformly distributed here. Let's say the objective is to estimate the theta. What is theta? Theta is the probability the point falls into a smaller subregion, smaller region here, A. Okay. So A is here, and this is the bigger set, and all we know is that x, y uniformly distributed in the bigger region. Okay, consider a raw Monte Carlo estimator. Generate x, y uniformly between 0 and 1, 0 and 1, easy, right? And check if the first generation, the first point falls into the region. No? Yes? Okay, if yes, add 1, then continue, right? So basically you generate n runs, and in each run you have a 1 or 0. So the estimation of theta hat, which is the area of A, right? Or the probability that this point falls into A, is done by the ratio of the number of points that falls into A divided by the total number of points that generated. Easy, right? Okay. This is the raw Monte Carlo estimator. So theta, again, theta is what? Theta is our objective. Theta is the probability that x, y fall into A. You can imagine that this raw Monte Carlo estimator is inefficient if A is extremely small. So each time you're throwing a dart on a board with a very small probability that you're going to fall into that interval. So this is proportional, the number of samples is proportional to the ratio between the two areas. So it's inefficient. So since A is small, compared to the unit square, most of our observations are going to be 0, right? So a large number of samples are required. Okay. How about we do it in a smarter way? The region A, let's do it in a way so that the region A is no longer rare with respect to the smaller rectangle R. Okay, so let's build a smaller rectangle which major rise are A. So A is no longer too small compared to R. So find the R that covers A. So the ratio between A and R is not too small, right? Alright. So the region A is no longer rare with respect to the small rectangle. So the desired probability is that is the desired probability, is equal to, applying the conditional probability, right? You have two cases. Conditioning on the case xy falls into R or not, right? So you have to have this probability. This is a law of total probability kind of argument, right? Easy. So in the first case, let's remove the second case, because if xy do not belong to R, then the probability xy belong to A is 0. So second is dropped. Okay. So this quantity becomes this quantity, and let's say we know the probability that xy falls into R, meaning we know the area of R. Okay. Given xy belongs to R, the point xy is uniformly distributed in R. Right? Because xy is uniformly distributed within a bigger region, but given that xy falls into a small region, xy is still going to be uniformly distributed. You can prove that. Okay. New estimator here. We're going to estimate this guy. How do we estimate this guy? Again, accept and rejection, right? Generate xy falls into R uniformly. Basically, we're only throwing darts in here. Forget about this area. We're throwing darts in here. And each time, if the uniform distribution in R happen to fall in A, count 1, otherwise 0. This is what I mean by this thing, right? This probability. So total number of points generated in R, total number of points that falls into A. This is no longer too small. Let's say 50% or something like that. Of course, the desired target is still small because there's this adjustment, right? This probability xy falls into R is the ratio between the area of R and the area of 1, the bigger square, right? Okay. What are we doing? We're not generating xy in the bigger region, but it is distributed uniformly in the bigger region. So what have we done? We changed the probability. We changed the distribution of xy. Xy is no longer uniformly distributed in the bigger region. Instead, our new xy has 0 probability in this region, but concentrated in this area. So we changed the underlying distribution of our random variable. We changed the distribution. I'll get back to this. So let me explain the general idea, general framework. Now I'll return to this to make connections, right? So what makes this example work is that we can determine the distribution of xy given that xy falls into R. Otherwise, this won't work, right? Okay. The main idea, we're going to modify the distribution of these random elements to make the event no longer rare, to intentionally make the event more likely. This is very similar to that previous example concerning the probability that L is greater than small l, but it's in a different way. Okay. Here is the general framework of it's called important sampling. The main idea here: sample more often from the important region. So here, what is the more important region? Sample more often in this region. I mean, in general, we do sample more often. We sample less often in the non-important region. In this example, is extreme. We only sample in this region, right? We do not even sample in the non-important region. This is the non-important region, this is the important region. But the general idea is that sample more often here and less often here. Okay. Consider a random vector, a random variable, doesn't matter. Let's say we have a distribution, density function. So this argument is valid for a random vector or random variable, doesn't matter, as long as we know its distribution. Suppose we're estimating a mu, and mu is equal to expectation of some h function of x. X can be a vector, x can be a random variable, it's okay. Okay, how do we compute the expectation? Expectation of hx is equal to the weighted sum, meaning integral of h function multiplied by the density function, that's it. Right? Or, if you have n dimension, this is going to be n-dimensional integration and involving the joint distribution. Want a direct simulation of x. This should be bold-faced though, to be consistent with this. When the direct simulation of x, this random element, is difficult, inefficient, either because it's difficult to simulate a vector or random variable having density. For instance, fx is not invertible, so you can't do inverse transform, or any other reason, right? For instance, it's just difficult to simulate a copy of x using this density. Possibly because f is too complicated, right? Or the variance of hx is too high. In our example, right, our variance of the indicator is high. Why I say it's high? The variance is equal to the mean. The mean is 10 to the negative 10, minus 10. The variance is the same, and the square root of the variance is the standard deviation, which is 10 to the negative 5, and it's too high, right? Or a combination of both. Then we do the following. Okay, here's the idea. Suppose there's a gx, another PDF, right? Another joint PDF, such that whenever fx is 0, such as fx is 0 whenever gx is 0. So, right? So whenever gx is 0, fx is 0 as well. You will see why this matters. Okay. So before I go to the next page, let me repeat.